Hello and welcome back to another episode of Math with Stone. Today we get to start rotational kinematics and rotational physics. So with rotations and kinematics, one important thing is that kinematics is a study of motion. We're dealing with that today. And it's not going to deal with forces. That'll be in a completely different video, and torque will be the force. So for this video, we are going to go over the definitions, the basic idea of what it is, and some of the formulas. So one difference between what we were doing before, if you have been following the entire, everything in my physics series, is before we had things spinning, and we called it circular motion, and that would be called a revolution. And here we're going to be talking about rotational items. The big difference between revolution or circular motion and rotational motion is that in circular motion, something is like going around something else. Whereas rotational, the entire thing is spinning. A CD, the entire CD disc is spinning. A wheel, the entire wheel is spinning. Whereas circular motion, you could be going around a loop, or you could be going around something else, but you are independent of the spinning thing, okay? So, we got some other vocab words to go over. Another one that we need to go over is angular displacement. All of the words that we are going to be dealing with previously with kinematics are going to be kind of like transformed and replaced slightly. So an angular displacement is how far that angle has actually moved. Okay, so typically it goes counterclockwise. So if I was going from this point to this point, so to speak, I will have displaced about 40 degrees. Which is now also going to be changing because degrees is not very, what's the right word? User-friendly, and a more user-friendly version is radians, okay? And there's a conversion for radians to degrees, and that it feels like it's not even a degrees. It's kind of like converting inches to feet or meters into feet, and that would be that a pi is equal to 180 degrees. Okay, so 1 pi is equal to 180 degrees, which means 2 pi would be equal to 360, which is kind of helpful because all the way around the circle, I think it's 2 pi r, is the entire circle. So that's where they came up with it, because 2 pi is essentially the entire circle. So this is the radian part, 2 pi, and that would be the degree part, 360. Other things we have to deal with is the relationship between the linear distance and the angular displacement. Okay, so there's a big difference between what we were dealing with linear displacement before. First off, angular displacement would be what we already talked about. How big is that angle? How much did it displace? If it went clockwise, it's negative. If it went counterclockwise, it's positive. All right. Linear displacement is the length of the arc. The arc, which is not what we have previously done in this class. When we talked about, if we were going from here to here or vice versa, you would connect the dots before and you would get the straight line. That would be the actual displacement linearly. But when we're dealing with rotational kinematics and rotations, we are actually referring to the outside edge. So this arc on the outside. So whatever that arc on the outside is, that part is what we are referring to for our length of the arc and actual displacement, the linear displacement, whenever you're dealing with these problems. All right? A formula for that, I don't like this one, but it is still the formula. It would be arc length. The arc length is equal to the radius times the radian measure of the angle, theta. Okay, so if you ever need to find that arc length out, it's just radius times radians. Done. And that's another benefit of radians. All right, so let's get through a few other problems. We got an example here for you before we get into some more vocab and pretty much just formulas after this one example. So a hipster spins a vinyl copy of an album you've probably never heard of on their vintage record and player. The record spins 10 times. Find the angular displacement of the record at that time. There's two different ways you could do it. You could think of this, well, it's spun around 10 times. The angular displacement is literally how many times around or what was the angle produced. You could do 10 times 360 degrees and get 3,600 degrees. You could also be more smooth and do 10 times 2 pi to get 20 pi radians. Okay? And this one would be the one that I would prefer because I prefer my answers in radians. They are a little bit easier to deal with. All right. While the record was spinning, a fly stands on the record 10 centimeters from the center of the disc. Find the length of the fly's path. So this is like the linear path, but it's really going to be going around in the circle because you got your fly here and he's going around. Each and every time he goes around, he has completed one circle, essentially, that had a radius of 10 centimeters. So you can do your arc length is equal to radius times radians. And we found out our radians was 20 pi, so our arc would equal our radius, which is 10 centimeters, times our radians, which is 20 pi. And then when you multiply those together, you end up with, if you use 3.14 for pi, 6.3 meters. That fly has taken a journey. By the way, probably should convert that to 0.1 meters. Just realized centimeters. All right, a few more vocab things. We got angular velocity, and that would indicate the speed of the angle displacement. So essentially, how quickly did you get to whatever degrees that is? All right, so that would be the angular displacement divided by time, and it is denoted by the Greek symbol, well, one of the two ways that you denote the Greek symbol, omega. Okay, so this symbol right here, omega, is angular displacement. All right, it is, the angular velocity. It is the displacement of the angle divided by time. All right, as you move forward, you're going to find out that if you do a right hand rule, if you curve your hand inward in the direction of the angle, like this picture right here, your thumb would indicate the force and the torque that is going to be involved, but that's a different video. Angular acceleration. Angular acceleration is denoted by a new symbol, alpha, is equal to the change in velocity divided by time. Okay, so just like before where we had acceleration is equal to change in velocity over time, same thing here, it's just you use a different symbol. Acceleration for an angle, angular acceleration, is equal to alpha, which is equal to the change in velocity over time, but the change in angular velocity. Now what that means is if you were thinking about a wheel spinning on the ground, if it started spinning and it was going, let's say, we're going abstract here, if it was spinning at 1 meter per second and you increased the speed to like 4 meters per second, that means that the angle that it was spinning at, this angle right here, would have all of a sudden increased because it would have to be spinning around the circle even faster. So that would be the acceleration of the angle. All right, we're not talking about the linear acceleration, we're talking about how this angle increased, because how far out you go from the circle would actually determine how big the distance is. If you have a small wheel, 1 meter per second might be really difficult, but if you have a really big wheel, 4 meters per second will be really easy to do. So that's why we talk about the angle when we're dealing with these, because the radius really determines how quickly you're going, how far away you are from that angle spinning around in a circle. All right? The units for angular acceleration are going to be radians per second squared, or 1 over second squared. I like radians per second squared personally. And then a few other things. The relationship between linear speed and angular velocity would be your linear speed would equal your radius, times alpha. And if we wanted the linear velocity, you would take your radius and you would multiply by your angular velocity. Okay? So, a few other quick things before we quit the video, and that would be just to compare how these are really just the same. We got the kinematic equations, we got the linear equations, and they are all the exact same. You just can replace the V for your omega symbol for angular velocity. You can replace your A for acceleration with your alpha for angular velocity, and they all tell you the exact same thing, so we're not doing anything different. It's just going to be taking it with a whole different perspective more than anything else. All right, that's going to do it for this one. Until next time, everybody, stay positive, and I will see everybody later, my friends. Bye.